So actually,
But I am saying otherwise there might be a master mathematician waiting at there.
so let's move ahead. One more property. And that's of the composition then. Okay, if you haven't done that, using that, basically we're going to prove lots of small corollaries. So what we're going to prove is that if I have roughly two integrable functions, then their composition is also integrable. Okay. Let me precisely mention it. Let's try to think about the proof.
Anja?
So there's a proposition. Suppose that G is G belongs to F. Just like space of Riemann integrable functions with respect to alpha on A to B. Okay. And then G of A to B is contained in another interval, which is C to D. So I guess G of means that okay, that's a set of all images of G in another interval. And F from it. Here there's stronger assumptions. And F is a map from C into D into R is continuous. Okay. Only Riemann integrability is not going to work actually. Continuous. So if H is F composition G, so it's going to be a map from. So like a G is going to throw A to B into C to D and C to D into R. So this is going to be a map from
A to B to R.
A to B into R. So if H is G composition, then H is integrable. H is integrable. Okay. Did you see limitation in this result? The limitation is that, not every two composition of every two integrable functions is integrable, but at least you need this guy, the first one. So if you want to compose, or if you compose something integrable with something continuous, the new thing is going to be integrable. So in other words, our task is what? Our task is to show that H is integrable on Riemann and Riemann-Stieltjes intervals. So for that, what we need to do? We'll be given an epsilon, and our task will be to find it. Imagine you have been given an epsilon. It's possible.
There is just partition in here.
And
There is just a partition in H for G.
okay. We need more construction. It's not that trivial actually. We need more constructions. Okay. So let me begin and let me introduce a number k, which is bigger than the difference. Difference of what? Okay. Why we need it? Obviously, is going to come up afterwards. It's a number k, which is a supremum of the values of x when x is in C to D, and the infimum of f of x when x is in A2, x is in C to D. Okay. Okay. That's a number. We're gonna keep it aside in our pocket, and we're gonna take it out whenever we need it. So it's a supremum. So it's like a k is a number which is the difference of supremum of the values of x and the infimum of the values of x on the interval C. Let's choose a delta positive such that this delta is smaller than epsilon. Again. And difference of f of x minus f of y is smaller than this guy. Epsilon over 2 times of b minus e. You know, these construction proofs are boring. So what you can do, you have to do it. Why we are doing it, why we are choosing epsilon in such a way, obviously you know well that it's going to make our life simpler afterwards. Okay? Whenever the difference of x minus y is smaller than delta. Okay, here's the question. Why we can do this basically? Why we can choose such kind of a delta? Why we can choose such kind of a delta? Absolutely. Yes, so it must be. And the domain is compact. So it must be uniformly continuous. It must be uniformly. Because of the uniform quantity you are able to on such kind of things. Okay. Now, since G is integrable on what? A to B, and we have epsilon with us, so we can find a partition for which the difference of upper and lower Riemann is very less. There are some chosen epsilon. Okay. So consider a partition P of x naught, x1, x2 up to xn. Just audit this proof as a fun fact, okay? Be a partition of the interval A to B such that the difference between UFP alpha and LFP alpha should be less than R epsilon, but that epsilon is delta square by 2. So since G is integrable, okay, since G is integrable for every epsilon you can find a partition. So in particular if I choose
G or F, you have chosen for F.
sorry, it should be G actually. No, sorry. It should be
Sir, we have a confusion over there.
which
Every F we can find for every epsilon we can find delta, but how are we sure delta will be less than epsilon?
okay. My point is this, that you're saying choose the delta, choose a sufficiently small delta, which is smaller than epsilon. Okay. Here's the point I think. Point is this. In this statement, epsilon is not the R epsilon, but epsilon is this basically. For this epsilon, we can find a delta. And we can find such kind of a delta which is smaller than this epsilon. This is possible, it's not something impossible. You can do that. Okay? Little bit of construction, just playing around with things. You know, in mathematics education, mathematics education is a fascinating area. This would be, and this is a whole area of research, that how you're going to present such kind of non-trivial things, maybe boring things, in such a way that that means makes sense and effective. But anyway, so I don't like. So it's like I don't like to be. So what I want actually, rather than squeezing the proof and the thing that you are learning up to your understanding, why not to build our understanding and make sense of and see the thing in its monstrous form or whatever that form is. So that's a bit non-trivial. Okay, there is no other way to explain. But at least the thing that, so what actually we are doing, I mean, so you want to have a finished product, and you are now creating the nuts and bolts basically, and then you're going to put them together. So that's what we are doing. Okay. So these are the nuts and bolts that we're going to use in the farm, the argument. You're going to see that this is going to sufficiently do the work for us. Anyways, for I from 1 to 2, let us denote Mi to be the infimum. So it's like the infimum for this partition. It's like infimum of f of x whenever x is between xi minus 1 and xi. Okay? Capital Mi.
So here the K is the same K that we have.
Yeah. Just think about it. Why we are able to do it? Because h is integrable. So for every chosen epsilon, so not h but g is integrable. For every chosen, no matter what number you choose, you can find a partition. So I'm saying, I'm choosing this number. Okay. So I can find a partition. Okay, and I will say that this partition is an Einstein partition. So Mi is supremum of g of x. You need to be careful. This Mi is the infimum of the values of x. And this capital Mi is the supremum of g of x on, so it's like, on the same each subinterval, you have three functions working on. So there is f, there is, there is h actually. You have to, yeah. Okay. xi minus 1, so that psi, and okay. And let me denote wi to be what? To be the infimum of h of x such that x is running between xi minus 1 and okay. Let's move ahead. I can define on this page, let's define it on the same page. That's okay. This is G, not F. And similarly, capital WI, J, capital WI is the supremum of the same lambda. Let's see that. What you can do. What you can do. Lots of construction, lots of transferring. It's like, toolbox is filled with constructions now, but there are more coming. All these things that we are defining and constructing, we're going to use them in a second. Okay. So, finally, when this author is writing finally here, I can feel that he's also feeling the same stress. So he's saying, finally. So that's the final thing I'm going to do. Okay, don't worry. You have constructed lots of things. And say, finally. Finally, that's the last thing. Don't worry. Not more coming. Final, that's the final construction. So it's like, finally, let I to be, I to be those indexes in Z. Why is saying that? Infimum of infimum of I is those indexes which are between 1 to n. Okay. And obviously you can assume that they are integers, so they are natural numbers. Okay, such that this capital Mi minus Mi is less than null. Okay. So on each interval, each subinterval, it's not necessary that the supremum of g of x and the difference of supremum of g of x and supremum of infimum of g of x on that subinterval should be smaller than delta. But there can be some instant actually. Okay, it would be a fun to think that is this set non-empty? Is it, maybe there is nothing basically. My claim is that is going to be non-empty. There are some instances for which this is true. So it may be true for all, but it may be true for some empty. And J is similarly collection of such instants which are between 1 to n for which Wi, Wi but Mi minus Mi is greater than or equal to. So it's like these two sets are going to partition the partition. Not going to partition the partition, but it's going to split the partition into two intervals where not intervals but like two parts actually. In those parts for which this is true, and those parts for which the opposite is true. And obviously their union is going to give everything.
Yes.
Okay? Huh? Why?
Next one.
So it's not partition basically. I'm not calling it for partition in inverted commas. It's not partition basically. Imagine, just think about it. I have partition P naught for which I have x naught, x1 and up to xn. Okay? Okay, or maybe on the interval HB. So I have a big partition here. Okay. So I'm gonna say maybe this condition on this interval, for example, maybe on this interval on x0 and x1, you can have you are going to have the infimum and supremum.
Yes.
Okay? Certainly they exist.
Yes.
So their difference exists. And delta is a number. So you have a trichotomy law which says that they can be related. So either it is going to be less than delta or it is going to be bigger than delta. In other words, this index, which is 0 for example here, is going to be inside not 0 but 1 because, oh yes, for 1 actually. So this 1 is going to be either in this set because for this instant either this is true or it's going to be in this set. And similarly, this second interval. For this second interval, you can have what? You can have the difference, and that difference can be either less than delta or
Greater than or equal.
so in other words, this 2 is going to either go into I or go into J basically.
Yes.
So in other words, in that sense, each of these basically numbers are going to go into either I or J. So I'm saying that okay, this set 1 to n can be partitioned into 2 parts, for which those instants for which this is true, and those instants for which this is true. That's what let's ask it. For your understanding. Consider this that delta times the sum of I in J such that xi minus xi minus 1 is okay, this expression. My claim is that this is smaller than or equal to sum of I belongs to J times xi minus xi minus 1. Would you agree that why this should be true? No. Times mi and mi have small bracket. You agree that this must be why this should be true?
Yes. Delta is. Is it S or delta?
It's delta. It's delta. So just keep in mind these two definitions. Okay. For J, you have this condition. So mi minus mi is greater than or equal to delta for each I in J. Okay. So this should be.
Yes.
In other words, okay, what you can do, right? To see it explicitly. So if I have a delta here, I can insert this delta inside somewhere. That's a hanging.
Yes.
Now this guy is same as this guy, while this guy is less than or equal to n. That's the sum. That's the equal. And this guy, now what is this guy? This guy.
Change G of its
Huh?
change G of its size.
Change in G of x.
The partition for H.
Can you see a relationship with this basically? My claim is that this guy is less than or equal to UG P alpha minus LG P alpha. Why this should be the case? Because just think about it. When you write this sum explicitly, you're going to have mi minus mi times xi minus xi minus 1. Okay? But over the whole partition from 1 to n, okay, while these are sum, so obviously this sum is going to be less than or equal to this sum. And this guy is strictly less than delta square over. Okay? And therefore, if I divide both sides by delta, because delta is positive, what we get is that this sum of xi and xi minus 1, when I is in J, is smaller than delta over and so finally we are here. H E alpha and H E alpha. I want to show that this is smaller than alpha. In other words, all this construction was just because of what will be this. This is going to be the sum running I from 1 to n of capital Wi minus small wi times xi and xi minus 1. That's what the definition is. And now you can split this into two parts. When I is in I, that's W capital Wi minus small wi, okay, times xi minus 1 plus I belongs to J capital Wi minus small wi times xi minus xi minus 1. Okay? Because I union J is whole 1 to n. So I can split this sum into two parts. Now, what is so there is something that is being said is that what is going to be the behavior of Wi minus this capital Wi minus small wi on the interval I? We know about it. In case of G, in case of G, because we derive from G actually. We know that in case of G what is happening. But what would be in case of H actually? What would be this in case of H? So we can do some scratch work. So W minus. One thing more. We are not going to have here xi and xi minus 1. We're going to have alpha of xi and alpha of xi minus 1. So replace wherever we are writing, especially in sums. xi and xi minus 1. Now you can treat this for Riemann in parallel proof, but very analog argument could be given for. Just replace xi by alpha of xi minus 1. So what we can say about this guy, I in the Sukkur Riemann